All right, students, welcome to the introduction of the concepts. I want to encourage you to just look at these, think about these, get your mind around these ideas, and this section will be tons easier, and I think you'll enjoy it. All right, shut that camera off. Now look, we're talking about exponential and logarithmic functions. Of course, we're talking about things growing. In here, the logarithmic scale, that would be related to earthquakes and so forth. We will be focusing this lesson on the exponential functions, but this is the entire, lesson 15. Okay, so we'll take it one step at a time. All right, we are talking about exponential growth. Now, this is an example of exponential growth. I've got the numbers 2, 4, 8, 16, 32. Now notice the numbers are increasing, but if I take the amount that's increasing here, between these two it's increasing by 2 and 4 and 8 and 16 and so forth. Notice that the amount that's increasing is increasing itself. Okay? So that's the idea of exponential growth. Sometimes you hear someone talk about geometric growth. That is what they're talking about. So we're going to take this idea and use it all throughout this lesson. Okay, when I talk about exponential growth, I'm referring to this relationship right here. Now let's review for a second. Remember, the 2 is the base. The 8 is the number. I'll just put a B for base. I'll put an N for number. And then the 3 over here, you can call it the exponent, but I call it the power. Let me move my arrow over here, okay? All right, so the 3 is called the power. Power. All right, here's a relationship. Y is equal to a to the x, the base a to the variable. That is why it's called an exponential function, because we're moving the variable to the power position. Here's another one. Y is equal to e to the x. Now the variable is in the power position, and we'll see what that does for us. Now look at these 3 examples down here. Now we know that 3 squared is 9. But what is 3 to the 2.1? Can I do that? And 3 to the pi. How could I do that? Because that number doesn't end. That's an irrational number. That is a very good question. Okay, 3 to the 2.1. Well, we could guess for a second. 3 squared is 9, 3 cubed is 27. To the 2.1, if we could do it, we think that that value would be closer to 9. Okay, we could do it on the calculator, and 3 to the 2.1 does give me a value. What about 3 to the pi? 3 to the pi. Well, now pi is 3.14, so we think maybe a number a little higher than 27. So here's the point. The point is that you can take a base to a power that's not a rational number. That idea is crucial in the understanding of exponential functions. Now, I just want to show you the general gist of exponential functions. Exponential growth, just like we saw the numbers, okay, they could be growing higher. Like let's just say 2 to the x. The values could be lower. They could be getting a lot smaller or decreasing. This would be like 1/2 to the x. As a matter of fact, we could do e to the x. Okay, we'll talk about e in a little bit. E is a number about 3. And e to the x, since it's greater than 1, is going to go like that. So this is the graph of y equals e to the x. Again, this is just a general, short, quick review. Now, the question is, okay, so I gave you a general function. F of x is equal to some constant times the base to a power. In this case, it was really 1 times 2 to the x. Are you telling me that we could take that function and move it to the left and to the right, up and down? We could flip it and we could stretch it, and the answer is yes, we can. So keep that in mind. Also, we could take functions and we could For example, look at this exponential function. It really is an exponential decreasing function, but what's a little disguised about it, it's flipped and it's moved up or down. And I'll show you how to graph these functions. I'm going to make a separate video on exponential graphs so that you understand that more in detail. But what you need to see here is growth, decay, another type of growth, another base, e to the x, and yes, you can manipulate the graphs. Okay, now I want to ease into this particular idea. It's called the natural base, e. E is equal to 2.71828, and it looks like it repeats, but really it stops after a while repeating. It is an irrational number. So my question is, what would e squared be? What would e to the negative 1 be? What would e to the 2.13 be? All right, could you do this in your head? Well, you could approximate it in your head. E squared, that's about 3, so 3 squared's 9, so you're going to think a little less than 9. E to the negative 1, remember that's a minus sign, so the base goes on the bottom. That's about 1/3 or 0.33, but since that number is less than 3, it's going to be a little bit more than 0.33. Now look at this, e to the 2.13. Well, that's e squared and then a little bit more. So that's about, let's just say that's 3. That would be 9, a little bit more. I don't know, we'll say 12. Okay, so this gives you a sense of how to compute with e. Okay, so here's my calculator. Could we do this on the calculator? Well, yes, sure. Now, there's 2 different e keys. I'm going to use this key right above the divide sign. So watch this. Second e, enter. There's the value of e. So could I do e squared? Yes. I could use my squared key. Okay, so there you go. Beautiful. That's like we thought it was going to be. Could I do e to the negative 1? Second e, and then I could hit this x to the negative 1 key to be fancy. And, well, yes, we thought it was a little bit more than 0.36. And how about e to the 2.13? So now notice what we're doing. We're doing irrational base to a decimal number. This is exciting, folks. To the 2.13. Now your calculator may not show it that way. It may give you a little caret. No problem. Okay. So here you go, 8.41, which a little bit lower than we thought it was, but we have the general ballpark. So this is how you could use the key to find e. Now we want to ask a simple question. Can you graph y equals e to the x? All right. Okay, I plugged in the values that we just did on the calculator, and now the question is, well, I should be able to connect these points. Now notice the graph keeps on going up and to the right, rises to the right, and here it's leveling off. It's trying to touch that y-axis there, but it's never going to do that. Watch the video on the graphs if you've not done that already, and that should make sense. So this is the graph. You should be able to tell everything about the graph of y equals e to the x. Now what I need to be able to do, I need to be able to do transformations of y equals e to the x. So let's do the top one. Okay, on the top one, notice that the horizontal asymptote went down 3. So I'm going to put my green line here instead of the green line here. And so my points are going to go all down 3, but they're going to go to the left 2. To the left 2. I should put another mark here, okay? So could I do that? Yes, I should be able to do that. I'm going to go down 3. 1, 2, 3 to the left 2. 1, 2. Down 3. 1, 2, 3 to the left 2. 1, 2. And I'll do this one also. Down 3. Down 1, 2, 3 to the left 2. Okay. So I was able to transform. This is g of x right here. Okay, could I do f of x here? Yes. Notice what's happening here. This minus means it's switching across the y-axis, and this means up 2. Okay, so notice how I did that. Let me erase this right here. Okay, I flipped across the y-axis. This went to here, that stayed there, this point went over here. But now I need to go up 2. So I'm going to go up 1, 2. I'm going to go up 1, 1, 2, and then up 2 here. Okay. Okay. Now you can use your calculator, but it's helpful if you can do that by yourself. Now watch my little video on the transformation game of y equals 2 to the x. Okay, folks, it's all about money to some people, but this particular part of the lesson really is about money, and it's about making money. And so I know you want to make money here. I'm going to use, for my example, a $100 bill. And now let me show you the power of compound interest. So here's an example. My example in this particular case is I have $5,000 at 6% interest. Now notice that I'm starting over here at 5,000, and as I get up higher here, this is just 15 years old, okay, so this is 20 years old. All right, I am making money, but it almost looks like a line, right? Okay, but look at this graph right here. If I've kept that money in for 60 years, each one of these dots represents a numerical value, the compounded interest. That is incredible. So let me kind of make that a little bit bigger. So again, the way compound interest works, it's an exponential function, and notice that it has a general shape of an exponential function, and each one of these red dots represents a numerical value that you can figure out on your calculator. The point is simply this. You may not think, in this case, if someone put $5,000 away when you were born, that you had a lot of money at year 18 years old, $14,000. However, if you kept that money in and no one told you it was in there, look, at age 60, you'd have over $150,000. Can you retire on that? Good question. So let's make sure we know how compound interest works. Like I said, it's about money. Now, let's just talk about simple interest for a second. If I had $100 and I get 10% of that money and I put it in the bank at simple interest in 3 years, how much money would I have? Well, I started with 100. At the end of year 1, I'd have $10. At the end of year 2, $10. At the end of year 3. So when I'm done, I will have money, $130 here. Simple interest. But now look, focus down here at the bottom. This is how compound interest works. Again, I had the same thing, $100. This represents year 1, year 2, year 3. This represents the beginning of year 1. So, okay, so $100 beginning of year 1. At the end of year 1, I get $10 because it's 10%. I'll have $110 at the end of year 1, the beginning of year 2. But at the end of year 2, I'm going to have that 10%. I'm going to have interest on the 110, not on the 100. So it's like interest on interest. Well, what is 10% of 110? That's 11. Now I have $121 at the end of year 2. Look at year 3. At the end of year 3, I'm going to take the 10% interest on this amount, which is $12.10, and I will end up with $133.10. Notice that it is more, okay? But if you leave it in there over a period of time, it's a whole lot more. So notice what I did is I did the 100 plus 100 times 0.10 for that amount is the same thing as 100 times 1.1. The second year I did that again. I could just write them twice. That's where that power comes into play. And that is the power of compound interest. I hope that helps you.